Hello to day 62, aspiring chemistry nerds. Welcome to week 3 of the solutions unit, where we're going to dig into the math-based part of the chemistry as well as hit some more concepts. You can see that in week 4, as we finish off the unit, you will also have your remote solutions unit test. Check that understanding. All right, cool. Today our target is going to be going after being able to explain the solubility difference between gases and solids, why they have those differences, and then figuring out how you can make a solution of any choice molarity and what the dilution formula is. So what you do is dig out your ETD, flip it open to day 62, and we'll be talking about some hot cocoa. Yeah. So if we look at this, I'm going to get rid of my big ugly head. You should be writing down the questions because it'll help you as you go off to your other college classes as well as high school classes to understand this stuff. I want you to sketch on this axis and explain your prediction for the solubility curves for oxygen gas versus potassium chloride solid. What's the graph going to look like? Why does it look that way? And then what are real world connections that connect to the actual lines on your graph? The second one's easier. It says how many grams of solute are present in 4.50 liters of a 3.00 molar hydrochloric solution. So pause me now, write down the questions, take a swing at them, see what you know, and then we'll come back together and do it in about 5 seconds for me. Not even. Cool. So now that you're returning back to me, one thing we should do is have these nice axes here, and I've got to figure out some things. One thing I got to ask myself is, what do I actually know? Last class, you did this cool lab, basically, or you would have, with Alka-Seltzer, which would look at solubility, and you get an idea of how to read solubility curves. So this would be looking at solubility, which would be the grams of solute, versus that in 100 grams of water, which is the same thing as 100 milliliters of water. And then what that's affected by is this thing called temperature, how fast the solution is moving. We do that in degrees Celsius. Now, the good news is potassium chloride should be easy at this point because, of course, potassium chloride, we're telling you, it's a solid. And just looking at it, it's made of potassium and chlorine. They're on opposite sides of the table. So this thing is shake, 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 made of a metal and a non-metal, which means it's a salt. And shake, 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 shake them ionic. This is an ionic substance made of those ions because we're shaking them, which means that if I take this and I put it in a solution, what's it going to do? It's going to easily dissociate. And we've already figured out with the solubility lab, or would have with the ETDs, that if I increase the temperature of my actual solvent and the solution, that means that the parking spaces in between those waters are going to get bigger and bigger, and they're going to bump into the potassium chloride more often. So that means that its solubility is going to increase. The solubility of it in the water is definitely going to go up, so it means you could fit more in it. So your line for the potassium chloride should be a nice straight line. It's got this wonderful positive slope because the faster the solution's moving, the bigger the parking spots are, the more solid you can park in it if it's a nice ionic substance. Then we would have done the Alka-Seltzer Lab, where we would have looked at CO2, but in this case, we're talking about O2. And O2, of course, is a gas at this temperature, right, at room temperature. Now, the thing that you can notice about that's two oxygens that are both non-metals. So what they're doing is they're actually sharing two pairs of electrons, and that means they're overlapping. So this thing is a molecule. And being a molecule, we have to worry about what kind of fight we have here. And the thing that we should notice is this is a fight between oxygen, and who's got greater electronegativity? It's a perfect tie, which means the electrons are going to spend the same amount of time around each of them, which means overall this molecule has got no charge. It's what we call, in nerdy talk, nonpolar. Now, the fact that it's nonpolar means it's not like water. So gases in general are gases because they don't have charges, like CO2 and oxygen gas and hydrogen gas. That's why they tend to form bubbles and bubble out of things and become gases. They're not attracted to other gases. There's no charges to attract it to other oxygen molecules. Now, if you drew this graph correctly, you would notice that it would go like this, right? That would be the oxygen gas. You can notice it's like the exact opposite, because with gases being nonpolar, they don't want to be in solution. If I increase the temperature, then that actually increases the space between the water molecules in the solution, and a nice nonpolar thing like oxygen can then just wiggle its way out of solution. As it does that, that means there's less of it parked, so I decrease solubility. As I make the parking spots bigger between the waters, it's easier for the oxygen gas to leave the solution. So hopefully you notice that their solubility in water is the exact opposite. Gases and solids are the exact opposite. Gases specifically have no charges for the water to attract to. And since there's nothing to attract to, that means they have decreased solubility, right? You should be able to go a further step with this and notice some other things. One thing is, one of these lines is straight and the other one is curved. Now, the straight line's pretty easy to figure out. It's a direct relationship where one's increasing, the other's increasing proportionally. But why is the gas one curved? Well, anytime you see a curved line, that means you're looking at something that's speeding up or slowing down. It's accelerating or decelerating, because you're going to take physics hopefully eventually, right? So one thing I can see here is this steeper line means that the colder it gets, that allows me to trap even more oxygen as it gets crowded in there. And then as it heats up, it's really, really moving, and so much of the gas will come out that it's not going to be able to hold much. So it's speeding up its loss of solubility, right? Or I could throw other questions like, hey, what if I had lithium chloride? What would its line look like? Well, one thing we know is it's ionic, right? And being ionic, that lithium chloride, well, it's going to, well, if I increase temperature, it's going to increase its solubility, right? So that means its line, of course, would fit on here. It would look more like the potassium chlorides, but would it be higher than it in its slope, a greater slope, or a lesser slope? How do I decide? Well, one thing I could do is figure out, well, lithium is actually smaller than potassium, so it's an even smaller scooter. So I should always think about size, shape, and charge. Lithium chloride would have a line that was even gentler in its slope because it's pretty good at parking at even low temperatures, just like another one called sodium chloride, which would be somewhere in between there, somewhere in this range likely. Because, of course, that's why the ocean, even our cold ocean, can fit lots of it in it. In addition to that, that means that a cold ocean could fit more oxygen in it, and fish would like that. That's why there's many fish off our area. So make sure that you're always thinking about the parking spots. Make sure you're thinking about whether it's a solid or it's a gas, because they have very different solubility patterns. If I had something like potassium nitrate or sodium nitrate, how would it differ? Well, it's bigger. It's an RV like we talked about last time, so its line would be a bigger curve because it would be facing things like the fact that bigger parking spots allow you to fit a polyatomic in there. Those would make really good assessment questions, right? Then, of course, you can always look at the PowerPoint that I provided if you can't read my handwriting and check it right there. That, of course, will be attached to the website as well. Now, normally we go and talk to our chem partners and talk about the most important thing, like real-world examples of how this affects it, because we all know this has nothing to do with real life. It's just chemistry. A really good one would be if you've ever fallen in the Cedar River. When I was a ninth grade teacher, we used to go down and we'd collect BMIs, little bugs in the river, to figure out how healthy it was. And it's loaded with bugs and it's loaded with salmon because if you ever fall in the river, it's freezing cold. And being cold like that means that it's crowded and it holds lots of oxygen in it. That's why the salmon come up here to lay their eggs, because then their babies can actually survive. They can avoid predators in the ocean too, but it's really high oxygen levels. And why does it have so much oxygen? Because the Cedar River is surrounded by a Cedar River watershed with a bunch of trees that shade it and keep it cold until you cut it down and put a Fred Meyer or a whole bunch of houses or a giant school in it. Then it tends to warm up and lose its oxygen, right? The BMIs, of course, are just as sensitive to oxygen. That's why we're using them as an indicator. Other examples. Let's say you go down to the Hood Canal or you go to the end of any river in the world where there's a bunch of cities with a bunch of roads and they get rained on and it warms up the water. In the Hood Canal, as well as other places where are surrounded by people, that water gets trapped in there and heated up by the high temperatures in the summertime, and then all the fish drown. They drown because as you increase temperature, the dissolved oxygen, the amount of oxygen that's in solution decreases, and, well, they have to breathe too. They just breathe with their gills, so a fish can drown. This, unfortunately, is happening all over the planet. As the earth warms and the water of the oceans warm, we're getting larger and larger dead zones. That's just one reason why it's happening. Increasing temperature, decreasing solubility. This also could affect simpler things, like you leave your soda outside, it gets warm, and it goes flat. Well, it goes flat because as you increase temperature, you decrease gas solubility, and it bubbles its way out. That's why they pressurize the can to force it in there, because the gas doesn't want to be in there, the CO2 gas. And then when you open it, it releases some of that pressure, but if you really warm it up, it'll come out even faster because there's bigger parking spaces between it, so the gas can wiggle out. Other really good examples, you tend to drink hot coffee or hot cocoa because, of course, coffee is a fairly non-polar substance. It's an oil. It doesn't want to hang out. It's an amine. It doesn't want to hang out in the water, so if you increase the temperature, you can get it to dissolve a little bit better because it breaks it down. That allows the sugar to go in as well. With that sugar, that's going to allow it to dissolve faster because you're giving it better parking spots. Cold coffee is not very good because it doesn't allow the solubility of the caffeine that's in there and change the flavor. Soda, of course, is at the other end because not only do you have to get the caffeine in, but you got to surround it by something like a nice gas. And the nice thing about the gas is the CO2 is also nonpolar. So is the caffeine that's in there. And, well, those are like substances, which helps it to stay in solution. Once it bubbles out, you can tell it changes flavor because you're losing some of the carbonic acid, which balances out the bitterness of the caffeine. But that's just chemistry, right? Biggest thing you should notice, we use hot stuff to dissolve solids like sugar fast, and we use cold stuff to trap gases. That's why bubbles form on the top of the hot thing. It's bubbling out. Other examples would be like you. You are a giant solution, and every time you take a breath, you're trying to shove oxygen that doesn't want to be in your blood into your blood. So the problem with that is you have warm blood. That means that your oxygen constantly wants to bubble out of you and kill you. But that's why we evolved these great things called hemoglobin molecules, where rust holds onto the oxygen and traps it inside of us, thereby keeping us alive. That's what we're learning about in AP Bio this week, too. Tiny bubbles in my cup, increased temperature, bubbles up. Tiny bubbles in your sink, makes it cloudy, makes you think. Yeah, I'll stop singing now. If you've ever filled your cup off of the sink, you will notice, especially at the high school if you're ever there, there's a ton of little bubbles in there. Those, of course, are chlorine gas bubbles. We treat the gas and pressurize the water with the chlorine gas to kill off microorganisms, but if you warm it up or release the pressure, then the gas comes out very quickly. Some of them are oxygen as well as CO2 as well, because you're giving it a chance to escape, just like a soda. Now, Pop Rocks is another good example. If you ever stuck them on your tongue and closed your mouth, your head can explode. Not really, but this is just the idea that there's CO2 gas trapped inside the sugar crystals. You put them on your warm tongue. The warm tongue increases the solubility of the solid sugar crystals because they're very polar. As they dissolve, then the gas can escape. It doesn't go into the solution of your saliva because it's non-polar. It doesn't have charges for it to hold on to the water, so it bubbles out. It's like a perfect solubility graph of solid versus gases. Now, normally we take a 1-minute break, but I don't get those anymore. So we're going back into the other ETD, which is a calculating one, which is where we're heading for a good chunk of this unit now. How many grams of solute are present in 4.50 liters of a 3.00 molar hydrochloric solution? Well, that's easy. You just figure out what you got and what you need. And it's telling you what you need. You need the number of grams of solute. So the end of this, I'm going to end up with grams of my solute, the stuff being dissolved. That's the hydrochloric, right? Minus the water. Then it's giving you a couple things. It tells me that I've got 4.5 liters, so quite a bit, and I got 3.0 molar hydrochloric. So which one of those numbers do I start with? Well, if I'm trying to get the grams, I probably want to go to moles first. And the one that has moles in it is the one that is moles per liter. That's why you always want to write it as 3.00 moles of hydrochloric in every 1 liter. That's the same thing as the molar, right? Get in the habit of making it moles over liters, and calculating is much easier. Then dimensional analysis to the rescue. When we do that, the first thing I'd want to notice is I want to get to grams. So I got to get rid of moles. I'm going to divide by moles of hydrochloric. I'm going to turn it into a G thing. That means that I can look at my periodic table and say, hey, 1 pile of hydrochloric, if you add it up, which you should pause and do it, is 36.46 grams. Pretty light molecule, right? That's going to kill off the moles and give me grams over liters. But I don't want liters on the bottom, so I got to put liters on the top. I need another conversion factor. Now, I don't have 1 liter of it. I've got 4.5 liters of it. Now, what do I write on the bottom? I don't have to write anything on the bottom, but if it makes you feel better, you can say in my 1 sample, I've got 4.5 liters, right? The key thing is the liters and the liters cancel, and now the only unit left is a G thing, which is exactly what you're shooting for. Gotta love the dimensional analysis. If you plug that into your calculator, it'll tell you it's 492.21 grams. Getting siggy with it, you got 1, 2, 3 siggy figgies. So it's going to go out to 492 grams of hydrochloric. And you can box that bad boy up, right? So the good news is the old skills that we used before, they work the same way. The only thing we're throwing in here is the liter part because we're dealing with piles that are inside of liters of solution, right? But don't let it freak you out. Now, before you move on, ask yourself, does that answer make sense? Yeah, if you think about what's going on and you actually draw it, this 3 molar solution had 3 piles of the hydrochloric floating around in 1 liter. Then I took that, I turned that to grams, but then I had 4.5 of those. So each one of those piles weighs about 36-ish grams, right? Almost 36.5. That adds up to that 109, and then I have 4.5 of those beakers because I got 4.5 liters. That's going to add up to like 492 grams. That's a lot of piles of acid because that's a big jug of acid, right? Always ask yourself if it makes sense. This animation and the steps for it will be on PowerPoint too. Now, normally we go over the Alka-Seltzer Lab, which we already did in the last video, ETD, and we look at the molarity worksheet, which will get some of those questions on your the one assignment for this week. The one that is the molarity dilutions and stoichiometric solutions. Yep. So if we look at the Alka-Seltzer Lab, the biggest idea of it is if you increase temperature with a gas, solubility decreases because gases are non-polar. So they can't hold on to the water, give it bigger parking spots, and it will wiggle its way out. It's the exact opposite of the solids, right? If we look at why that affects us, we can see it happening in basically we're making a miniature ocean. As CO2 that we pump out from burning things into our atmosphere piles up in the atmosphere, it shoves its way into the ocean. It runs into water, and it goes into solution as a stuff called carbonic acid. That being a carbonic acid, an acid dissociates, and it throws out protons. And when it does that, of course, that's what makes the pH of the ocean drop, and it becomes acidic. That acid then kills all the larvae and the shellfish and the coral, and then, all the people that survive on the fish that grow into adult fish don't have anything to eat, but that's why ocean acidification is kind of a big deal and why gas solubility is a big deal. As the ocean warms, one feedback mechanism of this is, the hotter it gets, the less gas it can hold, and that could allow some of the CO2 to bubble out, but it's not going to be enough to make up for all the CO2 that we're pumping in from our cars every single day. But hey, at least with the coronavirus vacation right here, less people are driving and flying, right? Now, the molarity worksheet number 1 would have had questions. We'll take a look at those in a different way. What I wanted to show you is this FET, because we're going to take a look at the idea of how volume and molarity are affecting each other. So I'm going to bring up the FET, and you can see the link for it right there at the top. If you go into it, the cool thing is I can switch what drink I want to make. I'm going to go with nickel chloride because that's toxic. This is measuring my concentration. I have to move it into it. If I shake a little bit of solute in there, you'll see that, it goes into solution, and it reads it on there for me. Shake a little bit more, and it gets more and more concentrated. Now, the cool thing is, if as I do that, I can get some nice clean numbers. Let's go for 0.620. That'll work right there. One thing I can notice with this is I can also add solvent. And I got a 0.5 liter right here. So what if I added another 0.5 liter and basically doubled the volume of the solution? Well, hopefully you can predict if I double the volume of the solution, if I add solvent, that's going to take it and halve the concentration. So as I increase volume, think of arrows with your fingers, then I decrease concentration. Kind of makes sense. That's an indirect relationship because I'm watering down. The other cool thing that you can see is as you remove that solution, you're removing equal amounts of the solute and the solvent, and the concentration doesn't change. That's why we can pour out of a beaker and not affect its concentration. Other things that we can see, of course, is if I take and I add a solution instead, that doesn't change the concentration as fast because you're not only adding solute, you're also adding solvent. Now, the other cool things that you can do with this is you can shake, and keep going with that. As you shake it in there, it'll get darker and darker because it's getting more and more concentrated until eventually a cool thing happens. As you do that, although this is more of a scooter, so you can fit a lot in it. Look at that. The parking lot's full. It's gotten saturated, right? I can solve that. I can build a bigger parking lot like humans do. Really cool things you can do, of course, is you can also evaporate it with this. As you evaporate, you take away that solvent, and you can see the concentration is increasing then, and that's what's happening in Salt Lake City, any salt lake that you have, but that's where all our salt comes from and forms a layer at the bottom. It's almost like this has to do with, Sol, Utah, and stuff like that. Cool. Now, that means that we can get out our notes, and if we look at our notes, we're looking at these things called dilutions. I was watering down my solution, changing its concentration. And I use dilutions all the time to make your solutions. This is the number one tool of any chemist and any scientist that has to use solutions, which is pretty much every medical career too. A dilution is simple. It's when you're adding more solvent to a stock solution to lower its molarity. You're watering it down. So you always, of course, are going to go and you're going to use this formula. It's M1V1, the molarity and the volume before, and they are, of course, next to each other because they are indirectly related. They're inverses of each other, is equal to M2V2. Now, the cool thing about this is what you're really doing here is you're setting the moles equal. It's all about the piles, right? So the volume units don't actually matter as long as the units are the same on both sides. So normally you guys would play around that FET and come up with this on your own. I just gave it away to you. The key thing is you're always going to start with a stock solution that's more concentrated, and then you're going to add water up to a volume to make it less concentrated but have more solution. You're diluting it just like you dilute something like orange juice in your fridge. Now, what's the relationship between the two? It's pretty obvious. If you increase volume, molarity decreases. And what this means, of course, is if I was to take that and graph that, that would be an indirect relationship. One's going up and the other one's going down. Imagine my fingers, one up and one down. I guess I could use my pen. There we go. Now, cool things about this, the dilution will always do the exact opposite to the molarity. It will go down in molarity because you're watering it down. We always water things down, make them less concentrated. So a good example of a problem that's like that would be this one. You should write down the question. It will help a lot on your weekly assignment. Set it up and ask yourself, what you got, what you need, right? So what we need is we need the new molarity. And the new molarity, of course, is called M2. What we've got is we got a whole bunch of data. It's telling us we got 55 milliliters of it. It's this much of a concentrated solution, and you're going to add 100 milliliters of it of this calcium chloride solution, right? So this is a dilution, so I'm going to use M1V1 is equal to M2V2, just like I do anytime I make a solution for you in class. I use this like every day. Now, key thing I can notice here, I got some variables. I got this M1. Well, that's the original concentration. It was 4.3, and that's moles per liter, or you can use the molarity. I'm going to write moles per liter because I like to have that habit. That, of course, is of the calcium chloride, but it's the only thing in here, right? Then I can see that I'm starting off with a volume. It's 55 milliliters. I can keep it in milliliters as long as it's milliliters on both sides. On the other side, well, I don't know M2 because that's the new molarity I'm trying to find. And, well, I do know the volume, but you don't want to jump the gun because you started with 55 milliliters of the solution and you're adding to it 100 milliliters of new water to that. That's going to bring it up to 155 milliliters total for V2. And that's where most people slip up, so don't be that kid, right? If you then use your algebra and you divide that out, throw the 155 underneath on the other side, you can divide both sides by it. Nice thing about it is you can use your units as your friend. Milliliters and milliliters disappears, and the only unit left is moles per liter, which is molarity. You'd figure out and get siggy with it. There's 2 siggy figgies, for the least accurate, so it'd come out to an M2 of 1.5 moles per liter, or molar, calcium chloride solutions. That's how easy dilutions are. It's M1V1 equal to M2V2, and just like when we did things like Boyle's Law, you find your unknown, and then you can reset to it, right? Algebra, it's your best buddy. You can also find that on my PowerPoint if you can't read my handwriting. Now, typically what we would do at this point is we'd see if we could use that, and we go through what's called a serial dilution, which is a pretty simple and handy tool in chemistry. And the idea is this. You start off with your starting solution. We'll say that this one is 2 drops of food dye in 10 milliliters of water. You can do this one at home with measuring cups and stuff. It's non-toxic. And we'll fake that that's a 0.2 molar solution. Then what you would do is you'd pour off 1/10 of it, 1 milliliter of it, of the solution, and then you'd add 9 milliliters of just water so that it came up to a new volume of 10 milliliters. And then you would calculate its new concentration. Then you would do it again in a serial dilution, where you take this solution, steal 1 milliliter from it, and add that, and then add another milliliter, and it would get lighter and lighter at each step in a series of steps, which is nice. Now, cool thing about this is that means you can calculate it. There's my M1, it's the 0.2. I used 1 milliliter of it. Then I added that to 9 milliliters of water to bring it 10 milliliters, so my new actual concentration, M2, would be, it'd be, 1/10 of it. Makes sense, I just jumped the decimal. The second dilution, if I start with that one, it's the same steps. I use 1 milliliter of it. I water it down to 9 additional milliliters to bring it up to 10. My new concentration would be 1/10 of that. And it would go each step until eventually you couldn't actually see any of the dye, and you can reach a concentration of 0. It's called water, right? Cool. Normally, of course, we would have this kind of homework coming at us, but those things will all be built into your simple 1-week assignment, which has got a lot more math into it this time. Please be aware that your solutions test will be during week 4. We're in week 3 now. Thanks for listening. Nerd it up good.